Hi there. While trying to learn geometry nodes, I was experimenting with something like this, where I can have an object follow a non-simulated water surface with the ocean modifier, and make it work whatever the shape of the object is. So I was experimenting with the Raycast node and some vector maths and thought we can make a render engine with this and have geometry nodes rendering the viewport. I saw something like this being done years ago with other software, so I decided to give it a try in geometry nodes, as you can see here. This is not the usual Blender camera. This camera is made with this node tree here, and it have its own render engine in it. With resolution options and the focal length. And have a light setup. With intensity, a fall of distance, color, and shadow casting. On top of that, it can render multipass. Like here we have an alpha channel, depth or mist pass, normal pass, UV pass, and I was working on this diffuse pass. So let's hop into new Blender scene and make this from scratch. So here we are in Blender. Let's delete those and delete the competition. Let's switch to geometry nodes. So basically the camera is the sensor and the lens, and that's what we'll be trying to make. Let's start with our sensor. So let's just get the plane and switch to geometry. The sensor will be as simple as a grid object, and for this we'll try to make something like this. This will be the general size of the sensor, and we will have a render resolution which we will use to divide the grid. So what we're trying to do is every face on this grid will be equivalent to a pixel on a real sensor. Now let's work on our aspect ratio. We divide x by y. So this here will give me my aspect ratio, and we divide the x size by to have the right y size. So now the physical size of the sensor will follow the resolution aspect ratio, and will always keep square pixels. Now as you can see, it's too dense. That's why I wanted to have something like this. So this is the percentage that we can divide by 100 and multiply each one of these. and use this as our final subdivision. Here we can easily change the density of our pixels. Now let's group these. So this first one will be the size as a float. This one will be the res x. And the percentage. Let's name this sensor. Give it dimension. Oops. Good. So I was saying the camera is a sensor and the lens, and in this case the lens is nothing more than a focal length. So we will have a focal length, and from the center of the sensor we'll move with the focal length distance to have a focal point, and from this point we'll try to draw lines to the corners of the sensor. Okay, so let's have a focal length first as an input. And wire it as an output. And because we will need the size of the sensor to draw those lines, we'll wire this out too. This will be size X, and this will be size Y. Let's give our camera a focal length, and we will start drawing those lines. We will use a mesh line in endpoints mode with only 2 points. So the first point will be the center of the sensor plus the focal length in C. Let's have a combined XYZ. We'll plug the focal length in C and use this as the starting point. And of course we need to join the geometry. This is our first line. Starts from the focal point, which is right here. So to go over here we'll have to shift X and Y to the corner of the sensor. So I will use another one, X, and use it as the end location. So this is equivalent to the size of the sensor, and we only need half of it. So we need a mat node, and we'll divide by 2. And here we have it. Now we'll do the same thing for Y. We divide it by 2, plug it into Y component. and we are in the corner. Now we need to add 3 more lines. Or maybe I should group this right now, yeah. We join geometry, have this here, so we don't have to deal with a lot of inputs later. And here, this will be the focal length. Size X and size Y. Now let's clone all of these. To have different line, but this time we reverse Y. We reverse X. No, X reversed but not Y. And here it is. Now let's try if our focal length is working. Size for the sensor and resolution. So our camera is ready. Let's call it geometry node camera, and let's move it to the side. And rotate it. So now we're gonna put some objects that we will try to render. Let's create new collection. We call it render scene, in which we put all the objects we want the camera to render. In real life, light rays will travel from a light source and hit objects, start bouncing around in every possible direction until eventually hit our eyes or camera sensor. And that's how we see the world, and it will be gathering information on its way. But this is very expensive to compute. That's why in CG we do it in reverse. We start from the camera, and if we hit an object somewhere, that's when we do other type of calculations to see if there's a light source shining on it or a shadow or stuff like that. And that's an oversimplification of how ray tracing rendering works. And this is exactly what we're trying to do. More precisely, we will cast rays from our focal point, passing by every pixel of our sensor, and if this ray hits an object somewhere, that's what that pixel is looking at. So let's do this. To have a nice visualization, let's use mesh to points node. An instance point on our camera. We will use just the output from the sensor to not have this point at the focal point here. Make them a bit smaller and move them to the faces, so every point will be in the center of each pixel for now. Let's get Raycast node. So the Raycast node will cast rays from our geometry starting at a source position toward a target geometry. So our source position will be our focal point, which we can get from this group. We already calculated it here. Let's make this an output. Let's get maybe our source position. The target geometry is the object we're trying to render. So let's get the render scene collection and use it as our target geometry. Now the direction, as I said, we will cast toward every pixel of our sensor. So we will need to use every pixel coordinate and subtract from it the focal point, which will give us this vector as a direction. And use position field, vector mat, now the Raycast node will give us as an output a boolean is hit, which will tell us if the ray did hit anything or not, if it did, in which position, and it can read the normal of the surface in that position and the distance from the source till it hit the point, and it can read an attribute. To see this result, let's clone this node, another copy because I want to keep those points on the sensor, and connect the position from the raycast to this point. So in other words, if any ray did hit an object, move that point toward that position. You can see we have an error here for instances because I forget to realize our instances, very important. Oh, and we have to subtract. And here we are. Let's increase the resolution to see better. And here we are. We can see our rays that were raycast and they're hitting our geometries. Now let's use is hit as a selection on these points that are on the sensor. So if any ray that didn't hit anything, we take off that point. Let's take off the wireframe, and here we have it. Let's increase the resolution a bit, and this is our halo render of our camera. This is kind of alpha channel of our render where we can see the object. Let's create a new collection for object we don't want to render. Move the grid. Let's get rid of the raycast. Now let's try to use the head distance as a radius for those points. Because we're using the distance as the radius, we can already see like a depth pass being rendered on our sensor. Good, that means it's working. Now let's try to save these informations as attributes. Okay, now let's get rid of this, and we will pipe our rendered results into named attributes. Use store named attributes node on the sensor, not the hot camera. The attribute we're doing is hit. We call it alpha pass. And here it is. Let's get a better resolution. Now I've noticed something. If we use face, we can have very sharp render if we want to. If we use edges, let's get the wireframe. The attribute gets calculated for every edge, so for every pixel the result will be the average or interpolation of them, which will give us like a free anti-aliasing. Good, so this will be our alpha pass. Now we can work on the depth or mist pass. We're gonna clone this node and use the distance as an attribute. The values are obviously very large, so we use the map range node. This here would be equivalent to managing your mist pass, starting depth. We can reverse it from here. And this is the mist depth pass. Okay, things are about to get messy, so give me 1 second to clean up the node tree. Let's frame this. Alpha pass. Depth. Mist pass. We can take those options as parameter in our render engine. Now let's make the normal pass. And try to numbers here. I'm not sure why the viewer doesn't show it in color. And this option in Blender of showing the attributes sometimes works, sometimes no for me. Okay, here's our normal, but you can tell they're not looking right. And even if you rotate the camera, the colors will change. And that's because the normals are being calculated relative to the camera. So this was a very hard one to figure out, and I kept googling back and forth like geometry node, how to translate between local and global coordinates, and after trial and error and testing randomly, I fixed it. And when I fixed it, that's when I understood what's the issue. So we're getting our object collection as relative. If we do original, it will mess up the raycast. It's because this camera as an object as a Blender item have its own transformation, and if we do original, it looks like it's being calculated like there is no transformation, because that's what we're seeing. So what's happening is our camera with transformation will be right here. So if we parent as objects to this camera and they set its transformation, I think they will be kinda faced this way, and that's how the normals are calculated. So to have the proper normal, we need to get back this transformation, which is the rotation of the camera and its position. The rotation is not an issue for the normal pass, but we need the position for the position pass later. I mean, that's how I understood it. And to do this, we get an object info, self object node, which is our camera itself, and get our rotation and rotate our vectors using that rotation. So switch this to earlier rotation, use our camera rotation, and rotate those vectors before giving them to the attribute. And this is how normal map is supposed to look like. If you want to try in cycles, this is cycle normal map, and this is our normal map. Now let's have something like this, where we can have toggles to select which pass we can render before we continue with the other passes. So we'll use the switch node, and when the switch is false, we don't render the pass, which means we get this and bypass this node that's not going to be executed. When it's true, we pipe this, so now if we switch to alpha pass, not sure what's happening, that's not alpha. Oh, I didn't change the name here. So if we take off this switch, it will not work, and we'll add those here. Now we have our toggles in the respective outputs. So this will go in here. Let's get another switch node for the dead pass. It is working. I'm gonna clone this to work on our position pass. So for the position pass, we obviously take the hit position, and that's the vector we can use. But as I said earlier, disable the normal pass and activate the position. Here it is. Now if we look at cycles position pass, this is how it looks. Ours looks a bit different because of the translation of the camera I was talking about earlier. So we need to adjust this, add a vector, not, and add the translation of the camera. So here it looks correct, except here because we're adding the camera location 0, and we can multiply maybe this by our alpha channel to cancel it, but I think it's less calculation if we use our hit boolean with the switch node. We want a vector switch, so when it's true we take the position, we calculate. When it's not, we keep at 0, and we control this with hit boolean. Yeah, this is cycle position pass, and this is our position pass. Looks the same. Now let's do UV pass. So for the UV pass, if you remember that Raycast node can take an attribute as an input, and it will read this attribute from the target geometry at the hit position. So we'll try to get the name it attribute as a vector, and we get the UV map. That's the attribute we're giving to the Raycast, and we will try to read it. Activate our UV pass. And this is kinda what the UV pass will look like. So the UV pass contains the X and Y coordinate in the red and green channel, and the Blender manual says that the blue channel is hard-coded at 1. So we have a separate XYZ and combine XYZ. Not sure why it's not in color over here. Oh yeah, this is a vector, and this needs to be a vector too. Yep, here it is in color, but it doesn't look right, and that's what we're trying to fix. So we'll have the X, the Y, and have 1 in the last channel, which is equivalent to blue. And this is how UV looks like, except this, because we're coding 1 here, and we're gonna use the same trick as this one here. So when it's true, we give this value. When it's not, we just 0, and we use the same hit boolean. And that's how UV pass. Let's activate all passes. We have alpha, the depth, normal, normal, position, and UV. Cool. This video got too long already and we still didn't work on the most interesting pass, the diffuse pass, with light configuration. With intensity, fall off distance, color, and shadow casting. So please meet me in part 2 of this video. Subscribe if you haven't already, cause you don't want to miss this. Look at this beautiful render. Who wants to use cycles or EV anymore?
La bougie.
I really hope you did learn something from this and see you in the next video.